So today, yesterday we covered strong normalization versus the simply typed lambda calculus. And I mentioned yesterday that I was going to try to give you, one presentation of logical relations, the standard one yesterday. And today I'm going to switch to a slightly different way of essentially doing the same sort of proof. But specifically we'll cover type safety today. So I assume that everyone here has done a proof of type soundness or type safety for the simply typed lambda calculus using progress and preservation? Yes? Yes? You better all have. More hands? Oh, okay, right, of course. Sorry, I walked in late. Okay, so we're going to prove type safety today using logical relations. Turns out you can do that. Let's write down a statement of type safety. Someone want to help me out? Type safety, type soundness. By the way, simply typed lambda calculus from yesterday is up on the top board with the usual call by value, small step semantics. So we want to prove type safety. What is it that we want to, how do we state that? We want to show that if a term is well typed, let's say if a closed term E has type tau, then it reduces to a value. Okay, that's actually strong normalization. That's even stronger than what I want. And I say that because I'm going to add recursive types to this language later on in this lecture, and at that point we won't have termination. Yes? I don't. Yes, and this is precisely my point. In general, what type safety should mean, or what we mean when we say type safety. There's this well-known slogan: well-typed programs do not go wrong. Right? Another way of saying that is well-typed programs do not get stuck. We don't want to get stuck, right? Like where you have something like true being applied to a lambda or something like that, or being quite false. That would be a stuck state, right? You can't, that can't produce any proof. And it's not a value. Okay, so in general, and the point I'm trying to make is the way that most of you are trained these days, and even I was, is, we get to of type safety as literally being progress and preservation. It is not. Progress and preservation is one method of proving type safety. It's a very syntactic, operational sort of method of proving what we actually want. And what we actually want is this property. We want to say that if a program is well typed, and let's say it takes a number of steps, some number of steps, 0 or more, to some E prime, then at that point in time, either E prime is a value, or there exists another E double prime such that E prime can step to E double prime. That is what we mean by well-typed programs do not get stuck. Okay? Here's a well-typed program. You've been running it for a while, or maybe you haven't even taken any steps yet. This could be 0, right? But at this point in time, at any point in time, either you have already reached a value, or it is possible to take another step. Means you're not stuck. Okay? Yes?
The type of E prime or E prime?
No, we don't. See, we don't need to. This is all we need. This is the top level theorem that we're interested in proving when we prove type soundness. When we use the method of progress and preservation to prove type soundness, there we always look at only one step of the option. Right? So let's think about progress and preservation, right? Let's write it down then. Progress says that if E is well typed, then we can always take one step, right? Then there exists an E prime such that. By the way, anytime I start writing too small, just tell me immediately. Okay? All right. And preservation says. Oh, yes, sorry. Then either, I'll just write val E to mean this wordy thing about something is a value. Okay? All right. So then either E is a value,
or there exists an E prime such that you can step to E prime. Right? And preservation says that if E is well typed and E steps to E prime, then E prime has the same type, tau. Right? And the point is that in progress and preservation, since we're always looking at one step, we have to sort of maintain, preservation basically, right? We have to prove that after every step, the type is preserved. And using these two theorems, or lemmas, we prove the theorem that we're actually interested in, which is this one, right? So we say that we want to show that if some E is well typed and E reduces to E, E has stepped all the way to E prime. Now we want to show that either E prime is a value or there exists an E double prime, right? So what do? We first go and use our progress lemma a whole bunch of times, and that tells us, we first go and use our preservation lemma a whole bunch of times, right? And that tells us that our E prime that we've gotten to here has the type tau, right? And then we can use progress, and we know that either E prime is a value or there exists another one. Yes?
This is a star. Okay, this is a star. Not a plus, yeah. So yeah, sorry if it's too small. It's a star, so it's 0 or more steps. Any other questions? Okay, so
we make the point that we're going to prove type safety directly using logical relations. We will not be using progress and preservation. All right? And by the way, right now we're working in a very simple setting. We're just working with a simply typed lambda calculus. But as you develop richer languages with richer type systems, sometimes, one issue with progress and preservation is that after every single step, you have to be able to type check your program. You have to be able to type check running programs. And sometimes, in order to be able to type check the running programs, you have to build a lot more stuff into your type system. At the end of the day, we only care about type safety. And so, the type system that you need in order to type check surface programs, the programs that a programmer can write down in your language, that system could be much simpler, depending on your language, than the type system, the enriched type system that you need in order to type check intermediate terms. And you wouldn't need to type check intermediate terms if you weren't using progress and preservation to do your proof. I just want you to keep that sort of as a mental note in the back of your heads, all right, for the future. All right, and we'll see a very, very simple instance of this when we get to mutable references in a couple of days. There's a distinction between the type system that you might need to write down to type check surface programs that a programmer can write down, and the type system that you need in order to type check running terms or intermediate terms. Okay, yeah?
I want the designers of the language to care about what they can say about intermediate programs during execution. So I want them to care about the complex type system that's the type, even if it's not shown to me as a use case.
The designers of the language or the program?
The designers of the language.
Of the language, yes, absolutely. So what I'm saying about the type system not needing to be so rich in order to type check intermediate terms, it's not that that the work required to prove type safety just disappears. It just moves somewhere else. The complexity moves somewhere else. But it's just a technical point that you should keep in mind when as you in the future when you design more complicated type systems to do interesting things. Perhaps you can get away without doing that and instead use a method like logical relations to prove type safety. I've done this in the past. So it's just an alternative. It's not that you have to do that. And my point then is that you, the designer of the language, will still have to think about what's going on with the intermediate terms in order to prove type safety. It's just that you will be using a different method or different device to do that. Okay? Which may not be any easier, but...
Okay. All right. So we're going to prove type safety. All right. So here's how we're going to approach this. We're using logical relations, again, a unary logical relation to prove this. I'm going to set this up slightly differently. We're going to define a value interpretation of types. So what we're going to do is for every single type in our, basically by induction over the structure of types, for the types in our language, we are going to write down when when values of the language belong to that type. Okay? So we're sort of building a model of types and sets. So let's start by doing this for bool. So what are the values that belong to the type bool? Okay. All right. Let's do functions. Okay. So what are the values that belong to the function type, tau1 or tau2? Lambdas, okay. So since it's tau1 or tau2, I better have lambda x colon tau1 here, right, to match this tau1 and some expression. And when does an arbitrary lambda behave like a function of type tau1 or tau2 specifically? Okay, so a function is something that you apply, right? So we want to capture how we use it. We want to capture its behavior. So we say, okay, if you give me some argument, some value v, that behaves like an appropriate argument of type tau1, then if I take that v and substitute it into the body of the lambda, e, right, basically after beta reduction, this expression will behave like an expression of type tau2. Yeah. Yeah. Good point. Okay. This is because we are in a call by value setting. Okay. So ultimately, when you have a lambda in your hand, at some point when the actual, you will be applying it to a value form. You will have already reduced your argument to a value. That's why. If we were doing this for a call by name, version of simply type lambda calculus, I would put for all e in e of tau1 here. Not just value? Okay, that's a very good point. Okay, so this is an expression right now, right? So I clearly can't just put v here. Fair enough? So I'm separating my definitions out so that I have to think about value forms separately from expression forms. And I think this leads to a nicer, more modular definition. So in particular, right now, I haven't told you what this is. So let's define this next. Was there another question, or can we wait? Okay. All right. Okay, so we're going to define the set E tau, all right, the set of expressions that behave like expressions of type tau. So when does an expression, an arbitrary expression E, right, this is an arbitrary type tau, when does an E behave like something of type tau? When it reduces to a value of type tau, exactly. So, sorry? Or when it loops, exactly. So I want to capture that looping phenomenon. So let's not insist that it evaluate to a value of type tau. We're going to say that if, so for all e prime such that e reduces in some number of steps, 0 or more, this is a star, to e prime, and that e prime is irreducible. I'll explain this notation in a second. Then we want to make sure that the e prime is actually a value of type tau. Okay, so by irreducible here I mean any expression that is either a value or is stuck. So irreducible simply means that there does not, that the that e prime cannot take another step. So irreducible of any expression is irreducible if there does not exist an e prime such that you can step from e to e prime. That's all. Okay, so that means it could be a value or it could be a stuck expression. All right. So what I'm saying is that you can take a whole bunch of steps, but eventually when you get to an irreducible state, you better have a value in your hands of the right type. that behaves like a value of type tau. Okay? Yes?
Can you motivate why stars both on the step of type safety and both the step and the E? I mean, my natural intuition is we work in like the one-step world. So why are we in the many-step world? Is it weaker or stronger? Like.
Well, so type safety in general should be, it doesn't matter how many steps you've taken till now, you should now be able to take one more step. That's why I'm starting. Okay? And here, I'm basically saying, take however many steps you need to take to get to an irreducible step, irreducible state.
Okay.
When you can't take any more.
Yeah.
Okay. So, any other questions? Yeah.
I mean, I'm assuming that, so, I mean, we have irreducible and value as different predicates because we haven't proved that they're the same.
Precisely.
Okay.
Yes.
So basically, we are saying that any expression, we don't know that this expression is going to reduce to a value. Well, it's a simply type lambda calculus, so you could say that it will reduce to a value. Let's try an alternative definition. We could have defined E tau like this. Any expression E behaves like it has type tau if there exists a V such that E reduces to V in some number of steps, and V belongs to V of tau. What is this definition doing? If we go with this definition, then we're saying that for an expression to, for us to say that an expression behaves like it has type tau, it must reduce to a value, and the value behaves like it has type tau. Exactly. Right. So if you swapped in this definition instead of this one, it would essentially be proving strong normalization, which is what we did yesterday, right? I was telling you that we were going to work with an alternative way of writing down the logical relation that, from yesterday in some sense.
But we add a small fix to make this normalization more unique.
I will add that. I just don't want to add it right now. Okay? I will add it in the second half.
Okay. So we're not going to do strong normalization. I just want to show you type safety. Okay. So now we have. So by the way, here I'm assuming that the values that I'm putting in here, we're building these value interpretations of types out of values that have this type. So syntactically, they're closed values. Right? So in a sense, whenever I have V tau and it contains certain values, I want it to be the case because the value has that type tau and it's closed. Whenever I write E tau, I want to put here I want to put an expression that is a closed expression that of type tau. Okay? Yes?
Can you recover preservation from this?
Recover the strict statement of preservation from this?
Yeah. So could you design a system that sets to some A-type values but then ends up in a Y-type value, something like that?
So somewhere in the middle, at an intermediate state. My first reaction is to say that why do you want preservation? You just want type 50. But I'm not sure.
Because you see here where we go all the way to an irreducible state. We don't even talk about the ones in the middle. Right? So at least with this definition, I don't think so. Okay? Or maybe you can. I've never tried it. I would need to stare at it before I say yes or no. Yep?
Irreducible. So irreducible right now couldn't. Okay, so what does this definition say? It says that we get to an irreducible state, which may be a value, or it may be a substate.
Then we say it must be a value. Right? So, I mean, you could sort of say, why didn't I just write V here? Well, because basically I'm trying to build a logical relation with which I can prove type safety. Okay? So what I'm trying to prove is that you take a bunch of steps and you get somewhere where you can't take any more, and then I will show you that this is, in fact, a value state that you've reached. It's not an arbitrary stuck state. Yes? Yeah.
Right? Yes.
And what is x? X is a variable.
Where? That's over here?
Yeah, so x is a variable.
X is a variable, exactly.
What is it? Is it a value or an expression?
X is just, well, it's an expression. But right now we're not, right now we're just dealing, it's not a closed value, right?
What is it?
X is not a closed value, right?
What is it?
What is it then? It's just a variable, so it's a form of, it's an expression of our language.
And since E is like the bigger thing, why did we write the second line, so for the lambda, why did we write it at the end, an element of E? Why didn't we write it like, I still don't get that.
Oh, why didn't we write B here?
No, this is a type also.
Ah, okay, so you're saying why not just do this?
Yeah.
Because that doesn't tell me anything. Here's what I mean by that. So think of this as a you're trying to write down the semantics of when expressions or values belong to certain types. When they behave like they have that type, they don't violate the assumption of what we mean when we say that something has a type. Okay? We're too used to writing down type systems and saying, oh, this is what this is. But like, think about it semantically, right? When we write down that some expression, if we can use the types, the typing rules of our language.
That E has type tau. What does that really tell us? In a semantic or operational sense. What does that tell us about what will happen when we run that expression? That's the question I'm trying to answer. Precisely. Yes. Okay. So I'm trying to say that, so what I'm trying to say here is that a lambda term behaves like it has type tau 1 arrow tau 2 if, when I give it a value that behaves like it has type tau 1, I get back an expression after beta reduction that behaves like an expression of type tau 2. Behaves like is kind of key here. By behaves like, I mean when you run it, it doesn't violate the assumptions that you have in your head about how this thing is supposed to behave. Okay? All right. So this is my way of saying that this is an expression that behaves like it has type tau 2. And then we've explained what we mean by that. An expression behaves like it has type tau if, when you run it, eventually when it gets to an irreducible state and you can't run anymore, you have in your hands a value that behaves like it has type tau. So it's kind of circular in some sense, right? Because now we go back to the value definition, but yeah, Michael.
This is on par with the SN form we used yesterday. It's just defining what we're attempting to prove. We haven't actually got to the mechanism of how we're going to prove that.
On par meaning? It is analogous to it.
These are our logical relations like SN was our logical.
Precisely. These are logical relations like SN was our logical relation. In particular, when yesterday we were writing SN tau E, this is the equivalent of that, right? E belongs to E tau. I should say. E belongs to E tau. Is exactly analogous to writing SN tau. Okay?
All right. Okay. Now, so far we've been working with closed values and closed terms. All right, so next let's talk about, just like we did yesterday, we needed to lift the notion of strong normalization, right? We first defined when closed expressions belonged to the relation Fn, and then we talked about lifting that notion to open terms. All right, so we're going to do an analogous thing here. Basically what I want to do is, I want to define a semantic notion. So here, you know, type safety judgment. E has type tau under gamma, right? I want to define an analogous semantic notion, which I'm going to write with a double turn cell here, all right? And I want you to read this as E is an open term, okay? And it behaves like, when given, so again, going back to the slogan from yesterday, right? Logical relations, the slogan is that if you give me terms or inputs that have a certain property, then I will give you back outputs that have that property, all right? Or if you give me related inputs, I will give you related outputs. Okay, so we're going to try to define the semantic notion of safety, of type safety. Okay, so here's what I want to do. First, let's talk about substitutions. Again, substitutions gamma, just like we had yesterday. We're going to define a set G gamma, okay, of substitutions gamma. This is going to start to look very familiar, such that, by the way, little gamma, just like yesterday, maps variables to values. We want the domains of the two gammas to be equal, like yesterday. And for all x in the domain of gamma, it better be the case that gamma x, the values that these variables map to, belong to the value interpretation, sorry, not of tau, of gamma x. Okay? So I'm trying to say, what are all the substitutions that satisfy this type environment? These substitutions map variables to values. The type environment maps variables to types. Okay, so we basically want to make sure that we have mappings for exactly the same variables in the substitution as we do in the environment. And then we want to say that each one of the values that we have in our substitution behaves like a value of the right type. The type that gamma says it should have, that big gamma says it should have, right? Okay? And now using that, we can define our notion of semantic type safety, if you will, which goes like this. Basically, we want to say that for all substitutions gamma that behave appropriately, like, you know, given a substitution that contains values of the right types, it should be the case that if we use gamma to close E, then we get an expression that behaves like it has type tau. Does that make sense? Questions? Yes?
So just quickly, our expression for closed expression.
Our expression relation is for closed expression. Exactly. So here we were talking about closed expression, closed values of closed expression. So this is the expression relation, closed expressions here, and now we're going to see it. Any other questions? Okay. All right, so now that we've
This, I claim that in order to prove type safety, here's the theorem that I actually need to prove. Or it'll follow, but let's just say it this way. If E type checks under gamma and has type tau, then E will semantically behave like it has type tau under gamma. That's how you should read that. Okay. Now, before we go any further and even start to talk about how we prove this theorem, why is that the theorem that we want for type safety? Okay. All right. And in particular, we can get once. So here's the really easy way of seeing it. Let's prove this corollary. Type safety, as stated over here, is simply a corollary once you have this theorem. So let's try to prove it. So we're going to try to prove this, given this. Okay? Everyone with me? Because once we have that, we know that this theorem is good enough to give us type safety. All right. So we are going to prove. Let me write corollary up there. This is the corollary we're going to prove. So let's see if this follows from this theorem. Okay? All right. So we want to show that. So here's the proof of my corollary. We say suppose. Or we're given that E is a closed term of type tau, and we know that E takes a bunch of steps to get to E prime, and now we have to show that either E prime is a value, which I'm now writing as val E prime, or there exists an E double prime such that E prime steps to E double prime. That's what we have to show. Okay? Well, let's see. All right, we know that E has type tau. Therefore, let's go use this theorem. This theorem tells us that, from the theorem, we know that under a closed gamma, E semantically behaves like it has type tau, right? Since E has type tau, E semantically has type tau. Good? Yes? Okay. So now we know that. Let's go look at the definition of this, of semantic type safety, right? Okay, so E doesn't have any free variables, right? Gamma's empty. Okay, so this definition tells us that you need to pick some substitutions, but we don't need to pick any substitutions because gamma's empty. All right, so this theorem then basically immediately tells us that gamma is empty, so E belongs to E of tau. Okay, so now, therefore, from this we can, just looking at the definition, we know that to E of tau. Yeah? Okay. Let's go look at the definition of that. What does that tell us? That tells us that for all E prime such that E gets to E prime, if it's irreducible, etc. Okay, now let's make an observation before we do anything else. We know that here we're given that E takes some number of steps to get to E prime. Yes? Either that E prime is irreducible or it's not. Fair enough? Okay. So this E prime, it's either irreducible or not. Let's take the case where it's not irreducible. If it's not irreducible, then by definition it can take another step. Right? So we've just shown this. In the case where it's not irreducible, we can take another step. Good. We're done with the not irreducible case. Now let's consider the case where it is irreducible. All right? So now we're considering the case where E prime is irreducible. Okay. So now let's go look at this definition, because it tells us something about what happens when E prime is irreducible. So now we know that E belongs to E of tau, and we know that E has stepped to some E prime that is irreducible. Therefore, we know that that E prime belongs to V of tau. So therefore, E prime belongs to V of tau. By definition, that means that E prime is a value, and we're done. By the way, could everyone just close their laptops? I forgot to say this yesterday. I think you'll get a lot more out of it, unless you're using it to take notes or something. Hope this doesn't make me unpopular, but yeah.
Can you prove that? To do this
Completeness different. Completeness makes more sense to me when you have a definition of potential equivalence, so we'll get to that tomorrow. Here.
I want just the converse of the theorem that we have here.
That if E semantically behaves like it has type tau, then it's type check.
definitions that we have on the board over here, they really have type safety just built in. Right? Okay. All right, so the main task then is, how do we prove this theorem? Right? Because we haven't really done anything yet. I've just shown you that if we could prove that, then we would have type safety. Okay, so let's push this up. And how would we prove that theorem? Induction on this typing derivation, right? Okay, so we have a bunch of cases. Again, let's do, it's going to bore you guys now, but just do it anyway. The case where we have true, just like we did yesterday. Okay, so now we want to show that true behaves like it has type bool semantically. All right? So let's just unwind the definitions. What happens? What do we have to do? We have to show this. Therefore, we say, suppose that we're given a gamma in G of gamma, right? We have to show that gamma applied to E, which in this case is true, behaves like an expression of type bool, right? Okay. Again, gamma applied to true is just true because true is closed, right? So this is equivalent to showing that true behaves like an expression of type bool. All right. So let's go look at what we need to do in order to show that E belongs to E of bool. All right. Looking at the definition, we have to show that for all E prime such that true steps to E prime if it's irreducible, etc. All right. So suppose true steps to some E prime that is irreducible show that E prime is in V of bool. Okay, but now we know that true steps to some E prime, but true is a value already, so E prime must be true itself, right? Therefore, all we need to show is E prime is, since E prime is true, we just need to show that true belongs to V of bool, which is immediate from the definition of the value interpretation of bool, right? Okay. So just wanted to unwind the definitions to show you how that goes. Okay. Now, I'm thinking, should we do, would you guys like to do the lambda case? How many people did the proof of strong normalization last night, the lambda case? Didn't get that one. Okay. All right. Maybe we should do this then. But you guys, come on, wake up, help me out. I don't like this. This room is way too quiet, way quieter than last year. Benjamin is smiling. All right. Let's do lambda. That might. Somewhere in the middle last year too. People are tired. Too much cock hacking. Okay. Here we go. Lambda x colon tau dot e.
Maybe we just had a better group last year.
We just what? Sorry, I didn't catch that. We hadn't what? I missed it. Okay.
I'm sure I was wrong.
All right. Okay. So we're going to prove this theorem here. By the way, let's just step back for a second, or let me just erase this before we wade any further into proofs. This theorem, right, which says that if E is well typed, then E semantically behaves like it has type tau. I keep using this terminology, semantically behaves like it has type tau, because we're doing a proof of type safety. All right? But when you do anything with logical relations, you're going to see a theorem of this form every single time. Okay? And the general form is, if E is well typed, then it's in the logical relation. what we've done over here is we've built a logical relation. We first explained when closed values and closed expressions belonged to the value and expression interpretations, and then we explained when open terms were in the logical relation. That's what that notation is, all right, if you read it in its most general form. So what this is saying, this theorem, is saying that if something is well-typed, then it belongs to the logical relation. This theorem is known as the fundamental property. It's called the fundamental property of logical relations. It's also called the basic lemma. So in papers that you read, you will see it called either one or the other of these. Okay, so whenever you do this sort of thing, you set up a logical relation, you always then have to go and prove a fundamental property, which basically tells you something about your logical relation being sort of internally consistent in some way. Okay, and you'll start to see what I mean by that a little bit more when we get to those binary logical relations. Okay, all right. So this is the fundamental property that we're proving. All right, so we're proving it by induction on the derivation of that, and we are going to consider the lambda case. All right, so what do we have to show? We have to show that lambda x colon tau 1 dot e semantically behaves like it has type tau 1 or tau 2. Okay, let's look at the definition. All right, we say suppose we are given a substitution, little gamma, right? So suppose gamma belongs to G gamma. We are required, since we're trying to show this, we're required to show that gamma applied to our expression behaves like it has the appropriate type. So we have to show that gamma of lambda x colon tau 1 dot e belongs to e of our type tau 1 arrow tau 2. Okay? All right. Someone tell me what to do next. Trivial step.
So we can simplify that substitution.
We can simplify the substitution. Let's push the substitution in. Showing this is equivalent to showing lambda x colon tau 1 dot gamma e belongs to e of tau 1 arrow tau 2. Okay. All right, so let's go see what we need to do in order to prove this. Let's look at the definition of e tau. Well, we have to say that suppose that our expression steps to some e prime, right? So suppose that this lambda, I'm really spelling it out, steps to some e prime in some number of steps, and e prime is irreducible. And now we have to show that the e prime that we have belongs to v of tau 1 arrow tau 2. This is very much like the true case, right? Okay, so now we already have a value, so that must mean that e prime is, in fact, the lambda term that we had, right? So showing this just amounts to showing that this lambda that we have, lambda x dot gamma e, belongs to v of tau 1 arrow tau 2. Okay? So how do we show that? What do we need to do to show that? Let's look at the definition of v tau 1 arrow tau 2. What does it say? It says that you get to have a value v in v of tau 1. All right? So suppose we are given a value in v of tau 1. We have to show that after beta reduction, when we have gamma e with v for x, right? Take the body of this lambda, that's what it says, and substitute v for x. We have to show that that belongs to e of tau 2. Now what? Substitution lemma. By the way, we haven't used an induction hypothesis yet, have we? Yes, since I'm pointing at it. Okay, so since we know that E is well typed, it has type tau 2 under this environment, under the extended environment, we know by the induction hypothesis that under gamma x colon tau 1, semantically, E behaves like it has type tau 2. Right? We get that from the induction hypothesis here. And this is a double turnstile. All right. So let's try to use that fact. Yes?
Create a new substitution by extending gamma with E for x.
Okay, so we have gamma, right? And we know that it's in G of gamma. And
This V that belongs to V of tau 1. So gamma extended with x maps to V1, what we want is to show that that satisfies the extended environment, gamma with x colon tau 1. And in order to show that, what do we need to do? Well, we just need to observe that the gamma alone belongs to G of gamma, and the V1 alone belongs to V of tau 1. We have both of those facts here and here, right? And that's all we need, looking at the definition of G of gamma. Okay, so we have this fact. So we instantiate this with this gamma, and note that we know that it belongs to G of the extended environment. Therefore, we can immediately conclude that if we take this substitution, gamma with x maps to V1, and apply it to this expression, that belongs to E of this type, tau 2. Sorry?
oh, I'm sorry. I'm sorry, Randy. You wanted to add how it's just you're right. The V over there. Okay. Okay.
So we have this fact. And this is what we wanted to show, which is exactly, yes, precisely. So this expression is just equivalent to that, right? So we could just do gamma E and then substitute V for x. So we're done. Yes?
That induction over the types, right?
We're doing wait for the
Over.
we're doing induction over typing derivation. Right? That's what
Okay. So tau 2 having, okay, so the derivation for tau 2 is being smaller type and therefore a subderivation. That's why we get to use that induction hypothesis. I'm just.
Yes, exactly. So
Yeah.
we have a typing derivation that ends with this, right? So the typing derivation that ends with this is a smaller derivation.
Yeah.
Therefore, we can apply the induction hypothesis
To conclude this, right? Okay.
But the types don't get smaller when you go up in derivation in the application phase.
They don't have to. Well, simply depends on the calculus. But we're not doing induction on the types right now. The bit where induction on types comes in, let's go back and stare at this for a second. This logical relation is defined by induction on the structure of types. Okay? Let's look at why this is well-founded. Here we define bool. We're defining V of bool. That's pretty easy. That's our base case, right? It doesn't use V of bool or V of anything or E of anything, right? Okay. The definition at function types is well-founded because it appeals to V of tau 1, but tau 1 is a smaller type than tau 1 or tau 2. So we're good there. And here it appeals to E of tau 2. It doesn't appeal to V of tau 2, so we're not quite sure yet. So let's go look at E of tau 2. If this was E of tau 2, then that means that it appeals to V of tau 2. But V of tau 2 is smaller than V of tau 1, right? Tau 2 is smaller than tau 1 or tau 2. So it's well-founded. Yes?
So I guess just to help coming up, when we go to recursive types, is it which part of this breaks down? Is it just well-founded as you just described, or is it the induction on the derivation?
It is the definition itself.
Okay.
It will be in the definition of recursive types. Yes.
There's something stopping us from defining V and E and D as inductive version of rule
With rules, you mean, yeah, sure, that's absolutely fine. That's just a stylistic way of, however you want to write. Absolutely.
Well, it's a bit more subtle. If you try to define this as an inductive definition with rules in core, it will fail because there is a non-negative, a non-strictly positive occurrence there.
Yes, ready. Yes.
So you really have to define it as by using by structural recursion over the types in a system like core.
Yes, and for that I'm going to refer you to, there's a chapter on normalization for simply typed lambda calculus in software foundations. Chapter that in full macro. Okay? And he goes through all the details of how you would formulate how normalization needs to be. And the same idea applies to all of the logical relations that we talked. Okay. All right.
So we've done the lambda case. This is actually the shorter case. The application case is a little bit longer. So homework for tonight. Okay? Try it out at least, just so, because you can't really understand logical relations properly unless you at least step through one or two proofs of at least a couple of cases. Yes?
Yesterday you said that the E1 proof tends to be easier than the N1 proof.
Yesterday I was talking specifically in the context of, lambda and application. I wouldn't say that in general. Yeah. And here, it's not that application is harder. Application is just longer, the proof, because you have two subterms, E1 and E2, and they're both going to need to get reduced to values, and just the way the definitions unfold, it becomes a longer proof. Right? Because ultimately you're trying to show that E1 applied to E2 belongs to the E relation, which says that, the application gets all the way to some value, so you have to look at a bunch of sub-expressions. Apply induction hypothesis twice. Yes?
What makes something a logical? It all seems like a more explicit way of doing, I think, induction loading.
That's basically what it is.
Okay. So it's just making induction loading explicit. That's a logical relation.
Induction loading?
Yeah, that you make the things you're doing here is you're making your induction
You're making your
hypothesis
induction
stronger.
hypothesis stronger. Yes, exactly. Precisely the point I was sort of emphasizing again and again yesterday. That this is giving you a way to strengthen your induction hypothesis.
It's sort of a recipe, if you said.
Yes. And in fact, the recipe to do so in the case of function types will be pretty much exactly the same every single time. Okay? Even when you add other features, you'll just be carrying around the other stuff. The lambda case will look very much like this. If you give me arguments that behave like you have the argument type, then after you do beta reduction, that expression will behave like it has the result type. Okay? All right. Let's talk about we'll come back to that. Okay, so what I want to do next is talk about recursive types. Actually, before we do recursive type, let's extend this. Suppose that we added pairs to our simply typed lambda calculus. Okay? We're going to add pairs. We're going to add expressions of the form first E, second E for projections. Of course, we'll have pairs E1, E2. The value forms will add V1, V2, and all the appropriate typing rules that you expect. All right? And again, small step evaluation semantics. So I want to write down, I want to extend my logical relation with pairs now. So when do values belong to the type tau1 cross tau2? When you have a pair of values, okay? Right. V1 belongs to V tau1, and exactly, V of tau2. It's a pretty simple extension. Nothing else changes, right? We've sort of modularly, we've separated out
the case for expressions and so on. None of that is affected. So a pair of values belongs to the type, behaves like it has type tau1 cross tau2 if b1 behaves like it has type tau1 and b2 behaves like it has type tau2. How about sums? Tagged sums. So let's say we add in left, in right, in left, e, in. Ah, that's the point I was trying to make. So let's ignore sums for a second. We haven't done e of tau1 cross tau2. We don't have to, right? Because we generically defined the e relation for any arbitrary type. So we don't need to go and extend that in any way. That still holds. Yeah? Okay. For the pair extension, not at all. There are certain places where, of course, once we add something like, in fact, when you add recursive types, the e relation will change because the whole model, the whole logical relation changes. It needs to get richer. Another time the whole logical relation changes is when you add mutable references. Okay, the whole logical relation, the structure sort of changes because you need to track more information essentially. Yeah, it has to, exactly, but it has to do with the circularities that crop up, right? Like when you have references, you can do cycles in memory, and things are basically no longer well-founded. But we'll get to that. Okay, so how about sums? Now we have in left, in right, and case. Okay, value forms. In left v, v, in right v. When does a value belong to a sum type? Behave like it has a type tau1 plus tau2? There are two cases. Okay, why are there two cases? There are two different possibilities of what value you can have, right? So a value can have this type if it's, let me write it here, if it's in left of v, let's write v1, right? Or if it's in right of v2. Okay, so when does in left of v1 behave like it has type tau1 plus tau2? Right? And then we just need to union that with in right v2. Right? So it's quite straightforward. Yes?
Would it be correct? V of T1 by E of T1?
V of T1 with E of T1? So all of these value interpretations and types that we've defined, V of tau is going to tau.
So in that sense, it's correct, but why would you do that? I think it'll just complicate your life in the proofs or something. Okay. All right. Okay. Maybe.
Yeah, a little bit, right? Look at this. This is tau1 cross tau2, which corresponds to conjunction. Here we have tau1 plus tau2, corresponds to a disjunction or a union. Okay. And what about functions?
This is essentially an implication, right? The style in which I wrote it, I put a dot there, but there's an implication there, right? If you give me a v1 of tau, type tau1, then I get something of type tau2, right? Okay. We're doing a model construction, exactly. We're just interpreting types as sets. Okay. All right. So now let's add recursive types. So how many people here are familiar with recursive types and fold and unfold? Isorecursive from TAPL. Okay, maybe I should ask how many are not, because I just want to know if I should spend 5 minutes. Okay, I'll spend 5 minutes. All right, so Recursive types. All right, so the reason we want to add recursive types to our language is because we want to be able to encode things like lists and trees. Okay? So something like, let's do a tree instead. So you can have a tree type in ML, right? And it could just be empty, or it could be a leaf, or it could be a node of a tree cross int. Let's say we're storing integers in the nodes, right? So if we tried to do that in our simply typed lambda calculus, what we'd kind of like is to be able to write down definitions like a tree is either nil, is either a leaf. So let's represent that with the unit type. I'm going to write 1 for unit type. Everyone okay with unit types? Okay. All right. Or I'm going to use a sum type here. So it's either unit for a leaf or it's a node. So it's a tree cross int. Right? So this type clearly, I mean, we're defining a tree in terms of itself. Right? This is clearly a recursive definition. So if it's a recursive definition, it would be what we basically need to do. Well, okay, let's understand the recursive definition for a second. Let me just write alpha for tree so I don't have to write out tree for every single time. So what this definition is saying, basically, is that tree is equivalent to this definition. So unit plus alpha cross int. Product type has priority, so I'll leave out the braces. So this is equivalent to this, right? And it's equivalent to if I basically take this whole equation and substitute it for alpha on this side, right? So we want, for this alpha, we want to be able to substitute unit plus alpha cross int times, again, for this alpha, we can again substitute the whole, we would again substitute the whole thing. So unit plus alpha cross int on the outside. So basically keep substituting for alpha, right? That's what this definition is shorthand for. Every occurrence of tree here, you basically substitute the whole right-hand side for that occurrence of tree again, right? And ultimately, the trees that we're interested in, we could continue this process in the limit, right? And we get an infinite tree, right? Okay, so what we want is we basically want to take, this is a recursive definition, we want to take a least fixed point. So for the tree here, let's try, everyone okay with fixed points? Sort of? Okay. All right. So let's write down the function f of alpha, whose fixed point we need in order to get a tree. Basically, it should be, well, let's write it like this. Here's a function on types that takes a type alpha. It's just my way of saying that alpha is a type, and gives you back the type unit plus alpha cross int. Right? And we want to take the least fixed point of that. So in general, what we want is, I'm going to write down mu alpha, f of alpha, for the least fixed point of any function of this form. Okay? So if this is the least fixed point of a function that takes a type alpha, then by definition, that means that it is equal to f of mu alpha, f of alpha. That's just by definition of what a fixed point is. Whenever you have a fixed point of a function f, it has to be the case that the fixed point is equal to f of itself. Okay? All right. Now, let me just write tau here for f of alpha for a second. Mu alpha tau is equal to f of mu alpha tau, but f of this, right, f of alpha, I'm saying let tau be equal to f of alpha, right? So this then is really equal to tau with mu alpha tau substituted for alpha. Yeah? So basically, what I'm saying is let's posit the existence of a fixed point, all right, at the type level, and we're going to write it down as mu alpha tau. And by definition of it being a fixed point, we have this equation that mu alpha tau is equal to tau of with mu alpha tau replacing alpha. Okay? All right. Now, basically, this is a recursive type. What we want to do is extend, so once we have recursive types of this form, how would we write down tree? We can write it down using this simply as mu alpha unit plus alpha cross int. So having a mu type, a recursive type in our language lets us write down, lets us define things like trees and lists and so on. Okay? All right. Now, here's the little technical bit. I'm going to add recursive types to our simply typed lambda calculus up there. So I'm going to add alpha type variables to my type language, and I'm going to add recursive types mu alpha tau. Okay? And in particular, there are two flavors of recursive types that you can add, in which you can have recursive types in your language. So one is iso-recursive types. Iso-recursive types is when this equation, let's just ignore this. Let me write it here for clarity. You can view this equation here as an isomorphism or as an equivalence. All right? And that essentially leads to two forms of recursive types that you can add to your language. So if you view it as an isomorphism, then that means that you need some sort of operation in your language to witness that the view is changing. So you have something of this type, and you wish to treat it as something of this type. You need to do something in order to shift the view. And we call that, we can call it an unfold operation or an unroll operation. It just unfolds the type in a sense for you. All right? And we have a fold operation that goes in the opposite direction. So fold and unfold witness this isomorphism. They allow you to shift views between these two types. There's another way of doing recursive types, which is where you don't treat this equation as an isomorphism. Rather, you treat it as an equivalence. That's called equi-recursive types. Okay, so iso-recursive types and equi-recursive types. We're not going to do equi-recursive types. In equi-recursive types, you don't need the operations. You treat it as an equivalence, and the type system basically has to do inference of about when you're shifting views. But I won't go there. Okay, so what we're going to do is add some operations. We're going to add fold E and unfold E to our language. And I'm going to erase the evaluation context we have here just so I have more room. Okay, so value forms. We are going to add fold V as a value form here. And this will become clear in a second. And so notice here, I should make this point before I move on. Fold is an operation that, given an expression of the expanded type, tau with mu alpha tau for alpha, gives you back an expression of the type mu alpha tau. And unfold goes in the opposite direction. Okay? So fold expressions will have type mu alpha tau, and unfold expressions will have the type tau with mu alpha tau for alpha, the expanded type. Okay? All right. In terms of evaluation context, we have the stuff before, and now we want to evaluate under the fold or the unfold till we get a value. So we have fold E, unfold E. Okay, and in terms of reduction rules, we add the following. When you unfold, so you get this down to a value, right? Sorry. Unfold, you get this down to a value. What value can be sitting over? Oh, I should show you the typing rule first. Let's go look at the typing rule first. All right. So under gamma, fold E has type mu alpha tau. if E has type tau with mu alpha tau for alpha. That's the point I was trying to make over there. And unfold is the converse. Unfold E has type tau with mu alpha tau for alpha if E has type mu alpha tau. So this expands the type and this sort of contracts the type, rolls it back. Okay. So in terms of the operational semantics, the only reduction rule we need to add over here is when we have an unfold of a fold V. And that simply steps to V. Okay? Yeah?
If we repeat the type, we make this definition by induction or description of types?
Yes, it's enough. I mean, not as exactly as it's on board right now, but everything that I'm going to show you with a slight tweak works for every person. Okay. All right. So reduction rules, we've added the typing rules we need, we've added that. That's about it. Okay, so great.
What are the value forms that we've added? Fold V. So fold V has type mu alpha tau. That's the form of value that we have for recursive types. So let's define V of mu alpha tau. What values belong to V of mu alpha tau? Yeah?
And like, why don't we need to add fold, unfold, V? I mean, why do we only need to add this selection?
Oh, fold, unfold V?
Because the fold is, if we have a fold E,
Yeah.
then don't we need to, how do we reduce a fold E?
Okay, so here's the thing. If you have a fold V,
Yeah, then it's a value, but if it's,
sorry?
if we have a fold V, then it's a value, right? So,
Yes.
but if it's a fold, unfold, fold, oh, I see, then we can...
You just keep evaluating under the fold
Yeah,
until you get to a
yeah.
value point. Yeah, do that. Right. It's sort of magic of what's happening.
All right. So what kind of values can we put here? Do we want to put here? Fixed points? Let's. What value did I just add? Right? We've been picking values out of this grammar right here. So fold V. Okay. When does a fold V behave like it has type? It has this recursive type mu alpha tau. Let's go look at the typing rules for a hint. If we had a fold V, the underlying V should behave like it has type tau with mu alpha tau for alpha. Yeah? So why don't we just say that? That's basically what we want. We want to say that V behaves like something of type tau with mu alpha tau for alpha. Okay, what's wrong with that? It's ill-founded, right? We are trying to define the interpretation of this type, but inside the definition, we are using the definition for a larger type. Okay, so this is clearly not well-founded. All right, what can we do? Okay, but I'm not going to do fixed points. Okay, we're going to do this using the technique of step index logical relations. All right? So far, and until 2000, I think, yes. Until 2000, so 12 years ago, logical relations were always defined by induction on the structure of types. And then extending them to settings where you had even recursive functions and recursive types and let alone mutable references, all of these more advanced features where you have certain kinds of circularities creep in and types start to get bigger. It was really hard to extend logical relations to those settings. And people did come up with logical relations that did that, but they were essentially denotational in flavor, and they used rather complicated math, functors, etc., in order to do it. Okay? Step index logical relations are sort of, okay, first of all, step index logical relations fall into this category of the operational kind of logical relations. So I just mentioned denotational logical relations, where you essentially interpret types using some sort of mathematical objects. You say V of tau is inhabited by some sort of mathematical functions, etc. Okay? We're not doing denotational version of logical relations. We're not doing denotational semantics. We're using a very operational flavor of logical relations. That's why you see, when does an expression E belong to E of tau? Well, let's go run it. Okay? That's going to happen over and over again. We sort of run things to see if they behave like the thing that we expect. Okay? All right. So now, step index logical relations. Basically, here the problem is that the types are getting larger. With step indexing, we're going to extend our logical relation slightly. We are going to say, we're not just going to say that some value V belongs to the value interpretation of tau. We're going to say that value V, we're going to put a natural number here, 0 or greater. This is our step index. And here's how you want to read this. Some value V looks like it has type tau for up to k steps. So if I give you a V that belongs to tau for k steps, you can go do anything with that value that you like, but you only have k steps within which nothing will go wrong. If you run more than k steps, if you try to do something with this value beyond k steps, then it may actually get stuck or not behave like what you expect. Okay? So I'm sort of approximating what I know. Yes?
What is nice about the system before the step index is that we can distinguish between error, like a real stuck state and a looping state. Right? But once we introduce the step index, then
well, I mean, it'll still work out. I mean, what do you mean by we can distinguish between a real stuck state and a looping state?
so let's say
That basically says that if you're looping, then I have nothing to show. Right? The definition of E tau says if I give you an expression and it just keeps looping, so then in order to show that that expression behaves like it has type tau, you don't really need to prove anything, right? Because if you look at the definition of E tau, it says for all E prime sets, so when you run E, you get to an irreducible state. Since your expression
yeah,
loops,
you only need to prove anything when it's looping. But now, the case where the k is
let's see how this works out. Okay?
Large case.
Wait, what?
You would use large case values.
Large case? Oh, you want me to write a big case? Sorry.
I mean, if you compute this interpretation with k equals 10,000, then all
Yes,
the programs.
yes, and actually that's the whole point. Eventually, what you want to do is, in your definitions, we want to define things at some, up to some approximation, but in the end, you want to do your proofs for all k. Okay, so let's see that.
So, read this as value V behaves like it has type tau for k steps. Let's go edit our definitions. When does a value behave like a Boolean for k steps? Or what are the values that behave like Booleans for k steps? It's true and false, right? We don't need to do anything else. Right? Okay. Now let's put a k here. I'm giving you, right? Ah, okay. That's what Benjamin is pointing out. And I was trying to avoid that for 2 more minutes. I will come back to that in a second. Okay. So basically what I've just done is I haven't put any arbitrary values here, right? I've put values that type check, right? I said this in the beginning that I'm always going to build these value interpretations out of values that syntactically have the right type. Okay? So that's why I only have true and false here. What Benjamin was asking is, why can't I put an arbitrary value, say that an arbitrary value is in there for 0 steps? I'm just not going to do that. I'll take care of that in a different way. So just hold that thought for a second. All right. So let's talk about when functions behave like they have type tau 1 arrow tau 2 for k steps. Okay. So you have a lambda term. You have I give you a lambda term. All right. What can you do with it? You have k steps to run. What can you do with it? To test if it's not a lambda. That's what you're doing here. Think of yourself as the adversary. I'm going to give you something and say you have k steps, and you're going to try to, do things with it to figure out, to make it, behave in certain ways and test if that assumption goes wrong. Okay? All right. So, have a lambda term. You have k steps. What can you do with it? Apply it. Okay, but you could either apply it now or at some point in the future, right? So in particular, you might be in the middle of a big program expression where you have a lambda being applied to some argument, and maybe your program needs to take some, you need to take some steps to evaluate the argument down to a value. All right, so you can, if I give you a lambda, you can apply it either now or in the future. Okay, I'm going to capture that by saying lambda x dot e behaves like it has type tau 1 arrow tau 2 for k steps if at some point in the future, when we have j possibly less than k steps left, if at that point you give me an argument that is good for the remaining number of steps, which is j, then after beta reduction, e with v for x should be good for j steps as well. Okay? All right. Now, when does an expression behave like it has some type tau for up to j steps? All right, so I'm going to put a k here. So an expression E behaves like it has type tau for k steps if what? Well, so k is the max you have. All right? So we're going to say, basically you're going to take E and you're going to run it for a while till it gets to a value. Right? So for some, suppose that for some j strictly less than k, suppose that E reduces to E prime in j steps. Okay, so I started out, I'm trying to figure out if this expression behaves like this type for k steps. I started out with k. I used up j of those steps to get to this irreducible point. Now how many steps do I have left? K minus j. So my E prime should behave like a value of type tau for k minus j. Okay? All right. Now, coming back to the point of what happens when you have 0 steps left. When I have 0 steps left, is this true? Sorry. Does true behave like a function of type bool arrow bool for 0 steps? Yes, it does. Okay, so in particular, then something like lambda x bool dot true looks like it has type bool arrow bool for 1 step, right? Because if I give you a lambda, this guy looks like it's a function for 0 steps. Okay, now let's make that the body of this lambda. Now you have a lambda. What can you do with it? You can apply it to something, right? In fact, I could, let me put a v here. I don't even need to put a v here. This lambda belongs to the value interpretation of this function type for 1 step. Why is that? Because you only have 1 step, so you can apply this to some Boolean value, and then you need to show that the body has behaves like an expression of type bool arrow bool for the remaining number of steps, which at that point will be 0. Okay? Oh, okay. Ask more. Okay.
With the current definition of k of t1 to t2, it looks like we may substitute in the body and then test for ej, which may be equal to k.
Ah, okay, good point. All right, so okay, we're defining this logical relation now by induction, by primary induction on these number of steps, and secondary induction on the types. Okay, so that's what we're doing. Keeping that in mind, let's look at what's going on and the well-foundedness of this bit of the definition. So we're trying to define the interpretation of tau 1 or tau 2 at k steps. And in the definition, we are using k, j, which could be k, because I put a less than or equal to here, right? So my point is that the step index might not get smaller, but the type gets smaller, so we're still okay. Alternatively, you could perfectly well write this definition with a j strictly less than k over there. Because if it's a lambda, you will always take one step before you need to, show anything. So that will work out fine as well. Okay, so here's one idea. I should draw this timeline. We're over here. We have k steps left. And we have a lambda. I'll just write lambda x dot. At some point in the future, when we have j steps left, actually let's say when we have j plus 1 steps left, someone gives us a value. And now we're going to take our lambda x dot e and apply it to that value. This beta reduction step is going to eat up exactly one step. And now you will have j steps left. Okay? So at this point, this expression will have stepped to e with v for x. That's what we have when we have j steps left. So now we just need to show that the e with v for x is good for the remaining j steps. With j equals 1? Yeah.
So if it's j less than or equal to k, then you can't prove that.
Oh, you're absolutely right. I was using j less than. Okay, yes, you're right. So let's use j strictly less than. But even if it doesn't work for the example, the logical relation is perfectly good even then. If you put a less than or equal to there. There's no problem with less than. Okay.
I have a question.
Yes.
So the timeline, or help me realize when I'm tripping on with the v case for lambdas, what's the equation for the j index on the v for tau 1?
So you expect this to be j plus 1?
I feel like it should be the difference between k and j plus 1. Like, at j plus 1, we got this v, and it seems like it should have taken some amount of steps with that to accommodate.
But you see, between here and here, someone else already took the steps. Okay? Someone else already took steps to get our argument down to a value. And this definition says, give me an argument that is already a value. Is that a problem?
That will behave like a value for j steps?
J is the number of steps you have left.
J is the number of steps that you have left.
I'm going to spin those evaluating the result of the substitution. So what does this have to do with?
Which may involve evaluating.
Which may involve evaluating the things plus.
So at max, it would be, at maximum, all those would be spent on j, or on the evaluating v.
On evaluating this value?
Right.
Well, this is already a value, right?
Yeah,
So don't worry about what happens.
Why does it need any steps at all?
Sorry?
So why does it need any steps at all?
Why does it need any steps at all? Good point. This comes back to why are we building a logical relation at all, in the sense that we, okay, what you're sort of saying is that this is already a value. What does the intuition about the remaining number of steps help with? Right? It's already a value. Why? I can't evaluate it anymore.
If it itself is a function, though.
Yes, this is analogous to what we were talking about yesterday with strong normalization. Why do we need to show that lambda, why do we need to worry about lambda belonging to the set well, because at some point you can apply that lambda, and then the body sitting inside the lambda is the thing that you will be able to run. That's the intuition. That's what this remaining j steps is for. So this function could be taking as its argument another function, and you could, yeah, this could be another function. And then inside here, you could apply that function. So you need to have some sort of, you need to control how many steps you have allotted for that to run. Does that help? Yeah.
Clear that we need one of those inclusions to be strict. Do we have a free choice of which one it is?
As in this one, or either the types can get smaller, or the step index.
One of the step indexes has to be a strict less than.
Yes, absolutely. So I always insist that this be strictly less than.
Would it break if we did it the other way around?
I'm not sure. I would have to test it out. Yeah.
How come 2 is the number of 0?
Oh, okay. So I claim that true belongs to, let's look at the definition. Let's see if we can show that true belongs to E0 bool arrow bool. In order to show that true belongs to bool arrow bool for 0 steps,
Find something smaller, like what?
there's nothing smaller than 0. That's precisely my point, right? So basically, you have to go and immediately pick a number smaller than 0. If given a number smaller than 0, you can show that, this reduces to, basically, since there is no number smaller than 0, it's factually true.
Okay. So you can put whatever.
Yes, you can put whatever there. So every term looks like it has any type whatsoever at 0 steps. And every term belongs to the position at 0 steps. Yes.
I'm actually confused about the exchange that Judy just had. So, what would go wrong if we let both of, is it a foundational issue that comes up if both of those are non-strict equalities?
Oh, if both of these are non-strict equalities?
Yeah.
Let's look at it. Okay, so this is a very, very good point. I should point this out. All right, so if this is a non-strict equality, right, then we have a k here. J can be equal to k. So we're examining whether or not this definition is still well-founded if this is less than or equal to this. Okay, so J can be equal to k. That means we have a k here, and in particular we have a k here. All right. Now we go here, and this is which looks fine, except when we add recursive types, we're not going to be fine. So let's add recursive types. Let's edit the definition of recursive types.
Excuse me?
Yes.
Just one question. I'm not so sure, well, this is a problem, but it seems to me like we are trying to define recursive types, but the definition we're using the natural numbers. So, the natural numbers will be defined as a recursive type. So
right, but this is sort of a meta theory, right?
Yeah.
Building a model. So
we're assuming we already
we're
know
assuming
the
we
natural
have
numbers,
the
and then we
natural
will build them as a recursive
Yes.
type.
We're not trying to encode the natural numbers themselves, these J's and K's. We're not trying to encode them themselves.
Yeah, you're assuming that they
You're
exist,
assuming
they're
that
well
they
ordered,
exist.
and
Exactly.
whatever.
Absolutely. Everything that you assume about natural numbers, absolutely.
We're also assuming that sets exists.
Okay, but what about the recursive type?
Okay. So I'm going to put a K here. This is why we added step indexing at all, right? Because this definition was not well founded. All right. So now let's try to figure out. Fold V belongs to this type for K steps if what? Right, we want to reduce the step here. So I'll just say for all J strictly less than K, V belongs to the bigger type for J steps. You could even put K minus 1. Yes, absolutely. So you could put J strictly less than K, or you could just put K minus 1. If you put K minus 1, you have to be a little bit careful in a proof later on. That's all. That's precisely where, yeah. Okay, so, sorry, what's your name? Gabriel. Okay, so what Gabriel just mentioned is that we want a form of monotonicity, right? I keep saying that V looks like
it has type tau for up to k steps. So if I give you a value that looks like it has type tau for 5 steps, should it look like it has type tau for 4 steps? Yes, because I said up to, right? And that intuition is captured by a lemma called, the type interpretations are downward closed, or it's a monotonicity property. Anytime we have V belongs to V tau for k steps, we have to be able to prove that V belongs to type tau for j steps for any j less than or equal to k. Okay? You can call it types are downward closed or monotonicity. We're going to have to prove this lemma. All right, I should let everyone go for lunch at this point. We'll continue with this tomorrow. All right?